All right, guys, today we're going to be looking at the derivatives of inverse trig functions. So this is 3.4. Let me get that in here. 3.4, and this is derivatives of inverse trig. So make sure you have that written in your notes and you are feeling it ready to go here. So when we are doing derivatives of inverse trig functions, there are a few different ways to go about it. First off, we can memorize them, which we'll go over in a second, but I always want for us to know, like, where did things come from? So the other thing that we can do is we can use Pythagorean theorem and use properties of right triangle trigonometry and implicit differentiation to derive these inverse trig function formulas. This very first guy right here, if we have y equals inverse sine of x, we can always think like, okay, what that means, if it's the inverse, we're like flipping the x and y value. So I can say x equals sine of y. When I use my implicit differentiation, let me get a new color here. If I take the derivative, so I'm saying d over dx, because this is the inverse of sine, right? I inverted those x and y values. The derivative of x is 1. The derivative of sine of y is cosine of y, but because we derivated y with respect to x, we leave that dy over dx in place. Last little bit is that I would solve for that dy over dx by dividing by cosine of y. And I can say dy over dx is going to be 1 over cosine y. Now let's talk about what that means here. In my original function, I know that when we are looking at this, I just have my triangle created here. We are looking for the inverse of sine, and it says that x is the sine of y. So if I look at my triangle, you guys might be like, where did these values come from? But if I were to draw this from scratch, I'm just going to call this unknown angle y. And if x is the sine of y, we know that sine is opposite over hypotenuse. So I'm going to label my hypotenuse with 1 and label my opposite with x so that it creates that ratio that we're looking for. Now, because of Pythagorean theorem, you know that x squared plus unknown squared equals 1 squared. So when I'm trying to find that unknown side length, I would subtract x squared, then take the square root. So that's where that value of 1 minus x squared comes in for that base leg. Going back to my problem, if I'm doing 1 over cosine of y, I know that cosine is adjacent over hypotenuse. And when I do adjacent, I'm looking at what's adjacent to that y angle. 1 minus the square root of x over 1. So going in and writing that in, dy over dx is going to be 1 over this square root of 1 minus x squared, because cosine of y is adjacent, so the square root of 1 minus x squared over hypotenuse, which is 1, which ends up just being 1 minus x squared. So all I did here was substitute cosine of y for that 1 minus x squared. This gives us our formula for our inverse sine. Let's check out cosine. So on cosine, these values look a little bit different here, because if we're rewriting this equation, we would say, all right, we're looking at inverse. So remember, we're inverting the x and y values. So I have x equals cosine of y. Cosine is adjacent over hypotenuse. So that's why in this case, we have x as our adjacent value, and 1 is our hypotenuse, because x divided by 1 is equivalent to x. And we can also think about this as like x over 1, right? So adjacent over hypotenuse. And then I determined this short leg. Same thing by Pythagorean theorem. You know that x squared plus the short leg squared needs to equal 1 squared. So same thing here. We subtract that x squared, take the square root, and that's where that short leg value comes from. Once again, I'm going to use implicit derivation. So I'm going to say d over dx. Remember, the derivative of x is 1. Cosine is going to be negative sine, but because we derivated y, we're going to leave that dy over dx. When I finish up and solve, I'm just going to rewrite this in standard. Dy over dx is 1 divided by negative sine of y. Now going back in and using using my triangle, I'm like, okay, I know sine is opposite over hypotenuse. So we have that square root. So sine of y equals O over h, which equals the square root of 1 minus x squared over 1, or the square root of 1 minus x squared. Going back into that formula, I'm going to say, okay, I'm substituting this guy in for sine of y. But remember that we still have that negative. Don't forget about him. So when I come up here and I finalize, I'm just going to move that negative to the numerator and say this is going to be over 1 minus x squared. We should notice that sine and cosine are almost identical. We know this. We play around with these rules, guys. So like they're pretty easy to remember. You have 1 over the square root of 1 minus x squared and negative 1 over the square root of 1 minus x squared. And always thinking about this, the derivative, thinking about the derivative of cosine. Remember, cosine decreases first. So I think about like that decrease is where that negative comes from, and your sine function increases first. So it's going to start off with that positive slope. Moving on to tangent, I'm going to do this guy really fast so we have time to talk about everything else. Flip those x and y's. Implicitly derivate. Remember the derivative of tangent of y is secant squared. Dy over dx equals 1. So dy over dx is going to be 1 over secant squared of y. Once again, when I'm talking about my tangent of y is x, remember tangent is adjacent, opposite over adjacent. My apologies there. So opposite over adjacent needs to equal x over 1. So that's why this opposite side length gets assigned x. This adjacent gets assigned 1. And using Pythagorean theorem, we know that 1 squared plus x squared needs to equal our missing side length squared. So then when I'm solving for that missing side length, you would just take the square root to get that canceled, and there's where that square root of 1 plus x squared comes from. We have secant squared of y. You know that secant and cosine are reciprocals, so when I go through this, I'm like, okay, I know secant is going to be, instead of adjacent over hypotenuse, it's going to be hypotenuse over adjacent. So in this case, that happens to be the square root of 1 plus x squared over 1. And when I plug in, or just the square root of 1 plus x squared, so when I plug this into my formula, you get 1 over 1 plus x squared squared, square root of. My brain was working a little too fast. Those cancel out, and we're just left with 1 over 1 plus x squared. We'll write that dy over dx right here. Once again, like most things calculus related, you can know how to do the long way, or you can memorize the formula and it provides a little bit of a shortcut. So I want to kind of go over some of these formulas really fast here, and some of these things we noticed. We noticed that when we were given sine of x, the numerator was the derivative of x, and we plugged in x squared. Same thing with cosine. The numerator was the negative derivative of x, and we plugged in that input, or that x squared. Same thing with tangent. Numerator is the derivative of x, which is 1, then we plug in that x squared. So let's start to develop a little bit of a trend here, and we're saying that if we take the derivative of the inverse sine of u, whatever the argument is, because they're not always going to be a beautiful, easy x, then the numerator of that derivative is going to be the derivative of that argument. So we're going to say, make sure that note means derivative. And then in the denominator, we take that argument and we square it. Same thing with my other values. For tangent, inverse tangent, inverse cosine, cosecant, secant, and cotangent. So let's kind of go through here and think of like the three things we need. We need to know what is u, or what is argument. We need to know what is the derivative of the argument. And we need to know what that argument squared would be. In this case, u, or my argument for this inverse sine, is 5x. So I'm just going in and saying, all right, according to this original equation, 5x is that input into sine. We know the derivative of 5x is 5, and we know that 5x squared is 25x squared. Instead of having to draw my circle instead of having to draw my triangle and saying like, okay, I'm going to reverse this. I know that this needs to be 5x over 1, and this is going to be 1 minus 25x squared with Pythagorean theorem. You can do all this. It takes longer. We could just plug into that formula and say, all right, I know that if I'm asked to derivate sine, so d over dx, I would get derivative of y is dy over dx. And the derivative of this inverse sine function, I'm going to say the derivative of u, which is 5, over the square root of 1 minus u squared, which is 25x squared. Put a box around it, and you are done. All right, very last problem we're going to go over is going to be, let's look at C, and I also want to do an evaluation on C. So I'm going to say at x equals, let's do 1/2. All right. So let's get this guy done right here, and I'll post the answers to letters B, D, and example 3 into the OneNote if that's something you want to go back and look at, but just be aware of like that will always be there for you. So we have y equals arc cosine of x squared, so same process. I'm going to say u is x squared, u prime is 2x, and u squared is x to the 4th. And then I'm just going to go back in and plug all this information into my cosine. I know that cosine is negative u prime. So when I took that implicit derivation, right, the derivative of both sides, I know that it's negative u prime, so negative 2x all over. And then we have the square root of 1 minus u squared. So square root of 1 minus x to the 4th. This would be like what the answer would be if it didn't ask to evaluate. But then when you're evaluating, we're going to evaluate at x equals 1/2. So I'm just plugging in that 1/2. So at x equals 1/2 would be negative 2 times 1/2 over square root of 1 minus 1/2 to the 4th. I kind of like ran out of room here. Let's just move this guy out of the way. When I'm looking at this guy now, we know that negative 2 times 1/2 is negative 1. And then 1/2 to the 4th, ooh, I should not have chose 1/2. Think like 1/2 times 1/2 times 1/2. So we have the square root of 1 minus, that's going to be 1 over 16. So we have negative 1 over the square root of 1 minus 1/16. I'm just going to call that 15/16. This doesn't really simplify any further. We could obviously like rationalize the denominator. It's not going to do much for us. Rationalizing the denominator would just give us negative 1. So this answer works. Rationalizing the denominator would give us negative 1 square root of 15/16 divided by 15 over 16, which in turn would give us 16 square roots of 15/16 over 15. So it doesn't do much to us, or if we were to get rid of that square root of 16, the other thing that could happen here is think about the square root of 16 is 4, so that would pull that 4 down to the denominator, and that could be 16 root 5 all over 60, and then we could simplify by a factor of 4. So know that these are all equivalent answers. The other thing, if I come back to my top guy right here, I could have negative 1 over square root of 15 over 4, or like times 1/4, right? So just kind of keep in mind like what all this kind of works out to be. And either way, any way I work this out, I'm going to get negative 4 some iteration of negative 4 over root 15 or negative 4 root 15 over 15 with that denominator rationalized. So just know that like some iteration will result. If you are asked to plug in a number, then you work with those rules first and then you substitute after.